how ice ages work, the cycles that shaped. Civilization, imagine standing in what is now New York City. But 20,000 years ago, instead of skyscrapers, a glacier towers above you is nearly 2 miles thick, covering everything from where you stand to the North Pole. The ocean is 400 feet lower than today. You could walk to what we call Long Island. Mammoths roam the tundra, where Central Park will someday be. This isn't science fiction. This was Earth during the last ice age. And it's not ancient history. It ended only 12,000 years ago, just before humans invented agriculture and built the first cities. In fact, every great civilization we know, Egyptian pyramids, Roman roads, medieval cathedrals, modern megacities, all of it happened in one brief warm period between ice ages. Today, we're going to explore one of the most fascinating and least understood forces that has shaped our planet, ice ages. We'll discover why they happen, how they've sculpted the land beneath our feet, and how they created the conditions that allowed human civilization to flourish. Most intriguingly, we'll explore whether we're living in an unusual warm period, or if the ice could return. By the end of our journey, you'll understand that the comfortable climate we take for granted is actually a rare and precious gift of timing. So let's travel back through time and unlock the secrets of the ice. Part 1. Understanding ice ages. What is an ice age? Really? Here's something that might surprise you. We're actually in an ice age right now. Yes, you read that correctly. The technical term ice age refers to any period when permanent ice sheets exist at the poles. By that definition, Earth has been in an ice age for about 2.6 million years, what most people call an ice age when glaciers covered much of North America, and Europe scientists call a glacial period. The warm intervals in between, like the one we're enjoying now, are called interglacials. These interglacial periods typically last 10 to 15,000 years. Our current interglacial, called the Holocene, has lasted about 12,000 years. Think of it like seasons. The overall ice age is like winter lasting millions of years. But within that long winter, there are brief warm spells, the interglacials when the ice retreats, then the cold returns, and glaciers advance again. This has happened over and over, like a pulse, about every 100,000 years. During glacial periods, ice sheets can cover up to 30% of Earth's land surface. During interglacials like today, ice is confined mostly to Antarctica and Greenland, covering about 10% of land. That difference might not sound dramatic, but it represents enough ice to lower sea levels by 400 feet and fundamentally reshape Earth's climate, ecosystems, and the possibilities for human life. The discovery of ice ages, a revolutionary idea, the idea that ice once covered much of the planet was once considered absurd. In the early 1800s, geologists found massive boulders scattered across Europe. Far from any mountains where they originated, they noticed scratches and grooves carved into bedrock. They discovered deposits of mixed rocks and sediment with no clear pattern. The prevailing explanation was Noah's floodsome catastrophic deluge must have carried these boulders and carved these valleys. But in 1837, a Swiss scientist named Louis Agassiz proposed something radical, a great ice age, when glaciers covered the land. His colleagues were skeptical, even hostile. The Earth, they believed, had been gradually cooling from a molten state, not cycling between warm and cold periods, but Agassiz had studied modern glaciers in the Alps and recognized that the mysterious geological features scattered across Europe matched exactly what glaciers do. They transport boulders, carve grooves in bedrock, and deposit mixed sediment, slowly. Evidence accumulated. Scientists found similar patterns on different continents. They discovered layers of sediment that could only have been deposited by ice. They recognized that valleys once thought carved by water had the distinctive U-shape created by glaciers. By the late 19th century, the Ice Age theory was accepted, revolutionizing our understanding of Earth's history. This discovery revealed something profound. Earth's climate isn't stable. The comfortable conditions humans evolved in aren't the planet's normal state. Climate can change dramatically, and has repeatedly. How much ice are we talking about? Let's put the scale of glacial ice into perspective, because it's genuinely hard to comprehend. During the last glacial maximum, about 20,000 years ago, the Laurentide ice sheet covered almost all of Canada and extended south to where New York, Chicago, and Seattle are today. At its thickest, it was over 2 miles tall, higher than 7 Empire State Buildings stacked on top of each other. The Scandinavian ice sheet blanketed Northern Europe from the British Isles to Russia. Smaller ice caps covered mountains worldwide. In total, these ice sheets contain 3 times more ice than exists on Earth today. All that ice came from water evaporated from the oceans and deposited as snow that never melted, accumulating year after year for thousands of years. With so much water locked in ice, sea levels dropped approximately 400 feet. The coastline was completely different. You could walk from Asia to Alaska across the Bering Land Bridge. Britain was connected to continental Europe. Indonesia's islands formed a single landmass. Florida was nearly twice its current width. The weight of the ice was so tremendous that it literally pressed the land down. Northern Canada and Scandinavia sank hundreds of feet under the ice's weight. Even today, thousands of years after the ice melted, these regions are still slowly rising back up, a process called isostatic rebound. Some areas rise about half an inch per year, enough to notice in a human lifetime. The Earth's climate through deep time to understand ice ages. We need to zoom out further. For most of Earth's 4.6 billion year history, the planet had no permanent ice at all. During the age of dinosaurs, about 100 million years ago, Earth was so warm that palm trees grew at the poles. There were no ice caps. Ocean levels were hundreds of feet higher than today. These ice-free periods, called greenhouse worlds, are actually Earth's normal state. Ice ages, or icehouse worlds, are the exception. Earth has experienced at least 5 major ice ages, each lasting millions of years, separated by much longer ice-free periods. The current ice age began about 2.6 million years ago, around the time the genus Homo, our ancestors, first appeared. This timing isn't coincidental. The climatic instability of ice age cycles, with dramatic swings between cold glacial periods and warm interglacials, may have been exactly the environmental pressure that drove human evolution, forcing adaptability and intelligence. Before this ice age, Earth was much warmer. Antarctica had ice, but the northern hemisphere had none. Then, through processes we're still working to fully understand, the planet entered a cooling trend. By 2.6 million years ago, it was cool enough for northern hemisphere ice sheets to form during orbital variations, and the ice age cycles began. The ice age cycle, a 100,000-year rhythm. Once scientists accepted that ice ages happened, they faced a new question. Why do they happen on a cycle? Why does ice advance and retreat with such regularity? The answer came from an unlikely source, a Serbian mathematician named Milankovitch. In the early 20th century, Milankovitch calculated that Earth's orbit around the sun isn't constant. It changes in predictable ways over thousands of years, altering how much sunlight different parts of Earth receive. He identified 3 main orbital variations, now called Milankovitch cycles. First, Earth's orbit changes shape from nearly circular to slightly elliptical, and back over about 100,000 years. Second, Earth's tilt varies between about 22 and 24.5 degrees over 41,000 years. We're currently at 23.5 degrees. Third, Earth wobbles on its axis like a spinning top, completing a full wobble every 26,000 years. Each of these changes affects how sunlight is distributed across Earth's surface and through the seasons. Critically, Milankovitch realized that ice ages are triggered, not by overall changes in sunlight reaching Earth, but by changes in summer sunlight at high northern latitudes. If northern summers are cool, snow from the previous winter doesn't fully melt. Year after year, snow accumulates, compresses into ice, and glaciers begin to grow. Milankovitch published his theory in the 1920s, but it was largely ignored. The astronomical calculations were complex, and scientists couldn't verify his predictions without accurate dates for past glacial periods. But in the 1970s, scientists analyzing ocean sediment cores found a perfect match between Milankovitch's predictions and the timing of ice age cycles. His theory was triumphantly confirmed. Why ice matters more than you think. Ice isn't just frozen water. It's one of the most powerful forces shaping Earth's climate, and it creates feedback loops that amplify small changes into ice ages. Here's the key. Ice reflects sunlight. Fresh snow reflects up to 90% of sunlight back to space. Ocean water, by contrast, absorbs 90% of sunlight. This difference is crucial. When ice covers more of the planet, more sunlight is reflected. Earth cools further. More ice forms. More sunlight is reflected, a positive feedback loop. This is why small changes in orbital cycles can trigger massive ice ages. When northern summers cool slightly due to orbital variations, some ice that would normally melt survives the summer. That extra ice reflects more sunlight. The next year, there's even more ice, reflecting even more sunlight. Over thousands of years, this feedback transforms a small decrease in summer sunlight into continent-covering ice sheets. The opposite happens when ice melts. Less ice means less reflection, more absorption of sunlight, more warming, more melting. This feedback helps explain why ice ages end relatively quickly in thousands rather than tens of thousands of years. Once melting begins, it accelerates. But ice does more than reflect sunlight. It stores fresh water, lowering sea levels and altering ocean currents. It weighs down continents, affecting tectonics. It grinds rocks into powder, creating soil. It carves valleys and shapes coastlines. Ice is, quite literally, a world-changing force. Part 2, the machinery of ice ages, the carbon connection. There's another crucial piece to the ice age puzzle: carbon dioxide. When scientists analyze ice cores from Antarctica, they find that CO2 levels and temperature are closely linked. During glacial periods, atmospheric CO2 drops to about 180 parts per million. During interglacials, it rises to about 280 parts per million. This presents a chicken and egg question. Does CO2 drive temperature? Or does temperature drive CO2? The answer is both, and understanding this is key to understanding ice. Age cycles. The Milankovitch cycles initiate changes by altering where and when sunlight hits Earth. But the temperature changes from orbital variations alone are too small to explain full ice ages. CO2 acts as an amplifier. As Earth cools, the ocean absorbs more CO2 from the atmosphere. Cold water dissolves gases better than warm water. With less CO2 in the atmosphere, the greenhouse effect weakens and Earth cools further. Similarly, when orbital conditions favor warming, temperature increases slightly. The ocean releases CO2, the greenhouse effect strengthens, and warming accelerates. It's another feedback loop, this time involving the entire carbon cycle. This is why ice core records are so valuable. Tiny air bubbles trapped in ancient ice preserve samples of the atmosphere from hundreds of thousands of years ago. These bubbles tell us that CO2 and temperature have moved in lockstep through multiple ice age cycles, confirming that greenhouse gases are fundamental climate controls. Here's the sobering part: current CO2 levels, at over 420 parts per million, are 50% higher than any level experienced during the past 800,000 years of ice age cycles. We've exited the range that has governed Earth's climate throughout human evolution. Ocean currents, the climate's conveyor belt. The ocean plays a starring role in ice age cycles, and not just through absorbing CO2. Ocean currents act like a planetary heating system, moving vast amounts of heat from the tropics toward the poles. The most important of these is the Atlantic meridional overturning circulation, part of which includes the Gulf Stream. Warm surface water flows from the Caribbean northward past the United States toward Europe. As it travels north, it cools and evaporates, becoming saltier and denser. Eventually, in the North Atlantic near Greenland, this cold, salty water becomes dense enough to sink, flowing back southward as a deep current. This circulation is why Western Europe is so mild despite being at the same latitude as frigid Canada. The Gulf Stream delivers tropical heat to European shores. London, at 51 degrees north latitude, has milder winters than cities in the northern United States, at 40 degrees north, but this circulation is sensitive to ice. During glacial periods, when massive ice sheets exist, they calve icebergs and release fresh water. This fresh water is less dense than salt water and doesn't sink. If enough fresh water enters the North Atlantic, it can shut down or weaken the overturning circulation, preventing warm water from flowing north. This has happened before. During the last ice age, there were abrupt climate events where temperatures in the North Atlantic region changed by 10 degrees Celsius or more within decades. These sudden shifts, called Dansgaard-Oeschger events, were likely caused by changes in ocean circulation triggered by ice sheet instability. The most famous example is the Younger Dryas event. About 12,800 years ago, Earth was warming, ice was retreating, and then suddenly, glacial conditions returned for over 1,000 years. The leading theory is that a massive meltwater pulse from North American ice sheets flooded into the North Atlantic, shutting down the circulation and plunging the region back into cold conditions. Mountains, continents, and Ice Age geography. Why didn't ice age cycles happen throughout Earth's history? Why only in the past few million years? Part of the answer lies in plate tectonics and the configuration of continents. For ice sheets to form and persist, you need land at high latitudes, where it's cold enough for snow to survive summer. You also need mountains to help generate precipitation. During most of Earth's history, continents were positioned differently, and conditions weren't right for major ice ages. The current ice age was set up by several geological events over tens of millions of years. The Himalayan plateau and Tibetan plateau rose to high elevations, affecting atmospheric circulation and promoting cooling. The Isthmus of Panama formed about 3 million years ago, closing the seaway between the Atlantic and Pacific Oceans. This altered ocean currents and may have strengthened the Gulf Stream, paradoxically increasing moisture delivery to high northern latitudes, which meant more snow and facilitated ice sheet growth. Antarctica's isolation at the South Pole, surrounded by ocean, allowed it to develop its massive ice sheet about 34 million years ago. The Arctic Ocean's enclosed geography, surrounded by continents, created conditions where ice sheets could grow. When the climate cooled enough, these geographic factors explain why ice ages are relatively rare in Earth's history. They require a specific arrangement of continents and oceans. Change the geography, and you change the potential for ice ages. The role of dust and aerosols. Here's a factor you might not expect: dust. During glacial periods, the climate was not just colder, but also drier and windier. With ice covering so much land and sea levels lower, more land surface was exposed. Deserts expanded. Strong winds picked up dust and carried it around the globe. Ice cores from Greenland and Antarctica showed dramatically higher dust levels during glacial periods. This dust came from expanded deserts, exposed continental shelves, and glacial grinding of rocks into fine powder. The dust settled everywhere: on ice sheets, on oceans, on land. This dust had climate effects. When it settled on ice and snow, it darkened the surface, reducing reflectivity and promoting melting. When it fell into the ocean, it delivered nutrients, particularly iron, which is often the limiting nutrient for phytoplankton growth. More phytoplankton meant more CO2 pulled from the atmosphere through photosynthesis. Some scientists have proposed that iron fertilization from dust may have helped draw down atmospheric CO2 during glacial periods, contributing to cooling. It's another feedback in the complex machinery of ice ages, showing how atmosphere, ocean, land, and life are all interconnected. Volcanic eruptions also injected aerosols into the atmosphere. While individual eruptions have short-term effects, sustained volcanism over long periods can influence climate. Large eruptions cool the planet by reflecting sunlight, potentially tipping conditions toward glaciation during vulnerable periods in the orbital cycles. Methane, the other greenhouse gas. We've talked about CO2. But there's another important greenhouse gas in the Ice Age story: methane. Ice cores show that methane levels also fluctuated with Ice Age cycles, though not as dramatically as CO2. Methane is produced by wetlands, where bacteria break down organic matter in oxygen-poor conditions. During glacial periods, with cooler temperatures and different rainfall patterns, wetland extent was reduced, so less methane was produced. During warm interglacials, wetlands expanded, releasing more methane. There's also a wildcard: methane hydrates. These are ice-like structures where methane molecules are trapped in water ice, found in ocean sediments and Arctic permafrost. Enormous amounts of methane are stored this way. If temperatures rise enough, these hydrates can destabilize, releasing methane to the atmosphere. Scientists debate whether methane hydrate release has played a role in past rapid warming events. The worry is that current warming could trigger significant methane release, creating a feedback that accelerates warming beyond what CO2 alone would cause. So far, large-scale methane release hasn't been observed, but it remains a concern. The interplay of multiple greenhouse gases, orbital cycles, ice feedbacks, ocean circulation, continental geography, dust, and more makes Ice Age cycles incredibly complex. No single factor controls them. Instead, they emerge from the interaction of many systems, each amplifying or dampening the others in a planetary scale dance that has repeated for millions of years. Part 3: Life during Ice Age's megafauna giants of the Ice Age picture. The world 20,000 years ago. Across the tundra and grasslands of the northern hemisphere roamed creatures. That would seem mythical today, Wooly. Mammoths with fur covering their massive bodies, and tusks curving up to 16 feet long. Woolly rhinoceroses. Massive and shaggy. Giant ground sloths as large as elephants. Saber-toothed cats with 7-inch fangs. Cave bears. Irish elk with antlers spanning 12 feet. These Ice Age megafauna dominated ecosystems across North and South America, Europe, and Asia. Many were adapted specifically to cold climates, with thick fur, compact bodies to retain heat, and specialized diets allowing them to survive on the sparse vegetation of glacial environments. The mammoth steppe, a vast grassland ecosystem that stretched from Spain to Canada, supported enormous herds. This ecosystem has no modern equivalent. It was more productive than today's tundra, but different from modern grasslands, sustained by the unique conditions of the Ice Age world: cold, dry, with intense seasonal variation. Then, beginning about 15,000 years ago, most of these magnificent creatures disappeared. Across the northern hemisphere, over 100 species of large mammals went extinct. By 10,000 years ago, they were gone. The extinctions were selective. Large animals disappeared while smaller ones survived. In areas where humans arrived late, like Australia and the Americas, extinctions coincided closely with human arrival. What caused these extinctions? Scientists debate two main theories: climate change and human hunting. The end of the Ice Age transformed ecosystems. The mammoth steppe broke up into tundra and forest. Some species couldn't adapt, but many extinctions happened rapidly, and similar climate changes in earlier interglacials hadn't caused comparable extinctions. The timing strongly implicates humans. We have evidence of mammoth hunting. These large animals evolved without human predators, and may have had no instinctive fear of us. A pregnant mammoth took nearly 2 years to produce a single offspring, making populations vulnerable to even modest hunting pressure. The truth is probably both climate change stressed populations, and human hunting delivered the final blow. Regardless, the Ice Age megafauna extinctions remind us that climate transitions are dangerous times for species, especially large ones with slow reproduction rates. Human evolution in an Ice Age world. We are Ice Age creatures. The genus Homo appeared about 2.6 million years ago, right when the current Ice Age began. The climatic instability of Ice Age cycles swinging between glacial and interglacial conditions every 100,000 years may have been the crucible that forged human intelligence. Think about it. Environments were constantly changing. Lakes appeared and disappeared. Forests became grasslands and back again. Animal populations migrated. Plants available for food shifted. A species facing such instability would benefit enormously from flexibility, problem-solving, and social cooperation. Humans evolved not to master one environment, but to adapt to many. Our ancestors weathered multiple glacial cycles. Archaeological evidence shows humans living in Europe during glacial periods, using fire, creating sophisticated stone tools, hunting large mammals, and making art. The famous cave paintings of Lascaux and Chauvet were created during the last Ice Age, showing that even in harsh glacial conditions, humans had the cognitive capacity for abstract thought and artistic expression. Different human populations, adapted to different Ice Age environments. Neanderthals evolved in Ice Age Europe, becoming cold-adapted with compact bodies, large noses to warm air before it reached the lungs, and sophisticated technology for hunting and survival. They endured tens of thousands of years of glacial conditions before going extinct about 40,000 years ago. Modern humans evolved in Africa and began spreading across the world about 70,000 years ago. During the last glacial period, they crossed into Asia, then into Europe, encountering Neanderthals. They reached Australia by at least 65,000 years ago, which required crossing ocean channels even during low sea levels. They entered the Americas via the Bering Land Bridge, probably around 15,000 years ago. Though the exact timing remains debated, as ages didn't prevent human expansion, they facilitated it. Lower sea levels created land bridges. Humans followed herds of mammals. The challenges of Ice Age environments selected for the traits that make us human: adaptability, innovation, cooperation, and culture, refugia where life survived during glacial periods. Ice sheets covered vast areas, but life didn't disappear. It retreated to refuge areas where conditions remained suitable. Understanding refugia helps explain patterns of biodiversity we see today. In Europe, the Mediterranean region served as a refugium, as ice covered Scandinavia and the Alps. Forests and the species dependent on them persisted in southern regions. When ice retreated, species recolonized from these refugia, which is why genetic studies often show European populations radiating from southern sources. In North America, areas south of the ice sheets served as refugia. The Pacific Northwest coast remained unglaciated, providing refuge for species. During the last glacial maximum, a corridor of ice-free land along the coast may have been how humans entered the Americas. Even within ice-dominated regions, there were ice-free pockets called nunataks, mountain peaks rising above the ice, supporting isolated populations. These served as tiny refugia, allowing some species to survive in the heart of glaciated areas. Tropical regions also changed during ice ages. With cooler, drier conditions, rainforests contracted into smaller refugial patches surrounded by savanna, or dry forest. This created isolated populations that diverged genetically, potentially driving speciation. The incredible biodiversity of places like the Amazon may partly result from repeated cycles of forest fragmentation and reconnection during ice age cycles. Refugia teach us that during environmental change, geography matters. Areas that buffer populations from the worst impacts become crucial for survival and recovery. As we face human-caused climate change, identifying and protecting potential refugia for species is a conservation priority. The oceans. During ice ages, while glaciers advanced on land, the oceans transformed as well. With so much water locked in ice, sea levels dropped about 400 feet. Continental shelves, now underwater, were exposed land. The geography of coasts was unrecognizable. Ocean temperatures dropped, though not uniformly. Tropical oceans cooled by perhaps 3 to 5 degrees Celsius, significant but not catastrophic for tropical species. Higher latitude oceans cooled more. The distribution of marine species shifted, with cold-adapted species expanding toward the equator, and tropical species contracting to narrow refugia. Ocean circulation patterns changed. With different coastlines and different temperature gradients, currents shifted. These changes affected nutrient distribution and marine productivity. Some regions became more productive, others less. Coral reefs, which require warm, shallow water, face challenges. Lower sea levels exposed some reefs to air, killing them. Cooler temperatures stressed corals. Reef extent contracted during glacial periods, though coral species survived in refugia and expanded again during interglacials. The biological productivity of oceans changed in complex ways. Colder water holds more dissolved oxygen and CO2, which can promote phytoplankton growth, but ocean stratification layering of water masses can limit nutrient delivery. From deep water to the surface where phytoplankton live, the net effect on ocean productivity during glacial periods is still debated. What's clear is that ice ages reorganized marine ecosystems as dramatically as terrestrial ones. Species migrated. Ecosystems shifted, and the ocean's role in climate changed. The ocean and the ice sheets were locked in a complex relationship, each influencing the other in feedback loops that drove the ice age cycles. Part 4. The End of the Ice Age and Birth of Civilization, the Great Melt about 19,000 years ago. Ice sheets reached their maximum extent. Then, driven by changes in Earth's orbit that increased northern summer sunlight, the ice began to retreat. This wasn't a smooth, steady process. Ice advanced and retreated multiple times over thousands of years, with dramatic regional variations. As glaciers melted, enormous volumes of water returned to the oceans. Sea levels rose about 400 feet over roughly 10,000 years, an average of about 4 feet per century. Though not evenly distributed, there were periods of especially rapid sea level rise called meltwater pulses, when ice sheets collapsed suddenly. The most famous is Meltwater Pulse 1A, about 14,600 years ago, when sea levels rose about 50 to 80 feet in perhaps 400 years, over a foot per century, drowning coastlines worldwide. Scientists still debate exactly which ice sheet collapsed to produce this pulse, with suspects including Antarctica and the Laurentide ice sheet. These rising seas reshaped coastlines, The land bridge between Asia and North America flooded, isolating American populations. Britain separated from Europe. Indonesia's connected landmass broke into islands. Countless coastal settlements, if any existed, vanished beneath the waves. Fresh water from melting ice flooded into the oceans, potentially disrupting circulation. The Younger Dryas event, that 1,000-year cold snap about 12,800 years ago, was likely triggered when a massive North American ice-dammed lake suddenly drained into the North Atlantic, shutting down the Gulf Stream circulation. By about 7,000 years ago, most of the great ice sheets had melted. Only Greenland and Antarctica retained their ice. Sea levels approached modern levels, stabilizing over the past few thousand years. This stability, coinciding with the development of agriculture and civilization, is not coincidental. How ice ages shape the land, look around you. If you live in northern North America, northern Europe, or other previously glaciated regions, nearly everything about the landscape was shaped by ice. The Great Lakes, the largest group of freshwater lakes on Earth, are glacial scars depressions carved by ice and filled with meltwater. The thousands of lakes in Canada, Scandinavia, and Minnesota are the same kettle lakes formed by melting ice blocks, or depressions carved by glacial movement. Valleys were transformed. Rivers carve V-shaped valleys, but glaciers carve U-shaped ones, wider and flatter. Yosemite Valley, fjords in Norway, many mountain valleys worldwide, all shaped by glacial erosion. Glaciers act like planetary bulldozers, grinding rock, carrying sediment, and depositing it hundreds of miles away. Those deposits, called glacial till, created the soil across much of northern regions, the fertile farmland of the American Midwest. The soils of northern Europe all are gifts of the Ice Age. Glaciers ground rocks into fine powder, creating mineral-rich soil. When the ice retreated, this fresh soil was ready for plants to colonize. Glaciers also created moraines, ridges of sediment deposited at glacier edges. Long Island and Cape Cod are terminal moraines, marking the southernmost extent of ice sheets. As you drive through formerly glaciated regions, you're navigating a landscape sculpted by ice-rolling hills, scattered boulders, sinuous ridges called eskers marking, where rivers flowed beneath ice. Even regions that weren't glaciated were affected. Enormous rivers carried meltwater from ice sheets, carving channels and depositing sediment. The channeled scablands of Washington state were carved by catastrophic floods, when ice dams failed, releasing glacial lakes in sudden, unimaginable deluges. The agricultural revolution timing is everything for 95% of human history. We were hunter-gatherers. Then, about 12,000 years ago, independently in multiple locations around the world, humans began domesticating plants and animals. This agricultural revolution transformed human society, leading to permanent settlements, cities, writing, and civilization. Why did agriculture develop when it did? And not earlier? Humans were cognitively capable of farming for tens of thousands of years. The answer lies in climate. Agriculture requires climate stability and predictability. You need to know when to plant, when rains will come, when to harvest. Seeds require specific conditions to germinate. Young plants are vulnerable to unexpected frosts or droughts. During the Ice Age, climate was unstable. Temperature and precipitation could shift dramatically within a human lifetime. In such conditions, farming is risky. Investing labor in planted crops could be a disaster if climate shifts destroyed them. Mobile hunter-gathering was more reliable. When the Ice Age ended, and the Holocene began about 12,000 years ago, climate stabilized, temperature and precipitation patterns became predictable. Atmospheric CO2 levels, which affect plant growth, rose from glacial lows. This stable, warm, CO2-enriched environment was perfect for agriculture. The earliest evidence of agriculture comes from the Fertile Crescent in the Middle East, where wheat and barley were domesticated, around 11,500 years ago. In China, rice and millet were domesticated about 9,000 years ago. In Mesoamerica, maize was domesticated about 9,000 years ago. In the Andes, potatoes were domesticated about 7,000 years ago. This explosion of agricultural development across the world, all within a few thousand years after the Ice Age ended, is striking. Climate stability enabled humanity's greatest transformation. Every city, every written word, every technological advance since depends on the surplus food that agriculture provides. which depends on the climate stability of the Holocene. Civilization in the sweet spot the past 12,000 years have been extraordinarily stable compared to Ice Age climate fluctuations. Temperature variations have been modest, perhaps 1 to 2 degrees Celsius globally. Even the medieval warm period and Little Ice Age, while significant regionally, were minor compared to glacial-interglacial swings. This stability allowed civilizations to flourish in the same locations for thousands of years. The Nile flooded predictably, enabling Egyptian agriculture. Mesopotamian cities depended on reliable rivers. Chinese dynasties arose in fertile river valleys. All this required climate predictability. We often think of climate as stable because it has been stable within human experience. But viewed on longer timescales, the Holocene is unusual, a brief warm period in an ongoing ice age. Ice cores show that past interglacials lasted 10 to 15,000 years before ice sheets began advancing again. Our current interglacial is about 12,000 years old. By natural cycles, we might expect it to continue another few thousand years before the next glacial period begins. But human activity has altered the equation by increasing atmospheric CO2 to levels unprecedented in ice age cycles. We've strengthened the greenhouse effect, potentially delaying or even preventing the next glaciation. This is complex. On one hand, without human influence, ice sheets would likely begin advancing, again within the next several thousand years. On the other hand, we're conducting an uncontrolled experiment, pushing CO2 levels far beyond anything the Ice Age climate system has experienced. The consequences are uncertain but likely include significant warming in coming centuries. Lessons from the transition, the end of the last. Ice Age offers lessons for understanding climate change. First, climate can change rapidly. Most of the glacial to interglacial warming happened over several thousand years, but within that transition were abrupt events: the Younger Dryas cold snap, the Balling Allard warming before it, meltwater pulses where change happened on timescales of decades to centuries. Second, feedbacks matter. Small initial changes, amplified by ice albedo feedbacks, carbon cycle feedbacks, and ocean circulation changes, produce dramatic results. This is why scientists are concerned about current warming, triggering feedbacks like permafrost thaw or ice sheet collapse. Third, ecosystems are vulnerable during transitions. The megafauna extinctions show that species adapted to one climate state can struggle when conditions change rapidly. The human-caused extinctions were probably facilitated by climate stress, making populations more vulnerable. Fourth, humans are adaptable. Our ancestors survived massive climate changes, multiple glacial cycles, and the transition to the Holocene. But there's a crucial difference. Past humans were small populations with simple technology. Today, billions of people depend on infrastructure, agriculture, and economic systems tuned to current climate. Adaptation will be more challenging at civilization scale. Finally, stability matters. The Holocene's climate stability enabled everything we call civilization. As we alter climate through greenhouse gas emissions, we risk losing that stability, potentially forcing adaptations far more challenging than anything our hunter-gatherer ancestors faced. Part 5. Ice Ages and Our Future. Are we headed for another ice age? This is a question many people ask, sometimes to argue that human-caused warming isn't a concern because an ice age is coming anyway. So let's be clear, yes. By natural orbital cycles, Earth would likely enter another glacial period at some point in the next several thousand years. But human activity has likely delayed or prevented this. The milankovitch cycles continue. Earth's orbit and tilt are still changing. The conditions that triggered past glaciations will eventually return. Without human influence, ice would likely begin advancing again, though probably not for at least another 1,000 years, or more based on current orbital configurations. However, we've increased atmospheric CO2 by 50% above ice age levels. This strengthens the greenhouse effect, warming the planet, even with orbital conditions favoring cooling. The extra greenhouse effect counteracts it. Some studies suggest we may have delayed the next ice age by tens of thousands of years, possibly even 50 to 100,000 years. This is a strange irony. Human activity that's causing harmful warming in the near term may also be preventing a glacial period. That would have been devastating in the longer term. But this isn't a reason for complacency. The warming we're causing now happens on timescales of decades to centuries. far faster than the millennia-long transitions between ice ages. The disruption to human civilization from rapid warming is a more immediate concern than preventing an ice age thousands of years in the future. What ice cores? Tell us about today. Ice cores from Antarctica and Greenland are time machines, preserving atmospheric history. The longest cores extend back 800,000 years, covering 8 complete glacial cycles. They've taught us invaluable lessons about how climate works. One crucial lesson, CO2 and temperature are tightly coupled. When one changes, the other follows. This relationship has held through every ice age cycle. It confirms that greenhouse gases are fundamental climate controls, not minor factors. Another lesson: climate can change abruptly. The gradual milankovitch cycles trigger ice ages, but within those cycles are sudden shifts, temperature changes of 10 degrees Celsius, or more in decades. These abrupt changes, recorded in Greenland ice cores, show that climate has tipping points, where feedbacks cause rapid reorganization. Perhaps most sobering current, CO2 levels are completely outside the range of the past 800,000 years. During this entire period, through 8 ice age cycles, CO2 never exceeded 300 parts per million. Now it's over 420. We've pushed the climate system into uncharted territory. Ice cores also show that interglacials, while more stable than glacial periods, still have variability. The last interglacial, about 125,000 years ago, was slightly warmer than the current Holocene, with sea levels about 20 feet higher. Studying this period helps scientists understand what to expect as current warming continues. Greenland and Antarctica, the remaining giants. Today's ice sheets are remnants of the last ice age. Antarctica holds about 90% of Earth's ice, enough to raise sea levels 200 feet if it all melted. Greenland holds most of the rest, enough for about 20 feet of sea level rise. These ice sheets are actively responding to current warming. Greenland is losing ice at an accelerating rate. Satellite measurements show mass loss has increased from about 34 billion tons per year in the 1990s to over 280 billion tons per year in recent years. Summer melting has intensified, and glaciers flowing into the sea have accelerated. The surface of Greenland's ice sheet is darkening as warmer temperatures reduce snow cover, exposing older, darker ice and promoting algae growth. Remember the albedo feedback: darker surfaces absorb more sunlight, causing more melting. This feedback is now actively operating on Greenland. Antarctica is more complex. East Antarctica, the largest portion, sits on land above sea level and has been relatively stable. But West Antarctica and the Antarctic Peninsula are losing ice rapidly. The peninsula has warmed several degrees in recent decades, causing dramatic ice shelf collapses. West Antarctic ice sheets rest on bedrock below sea level, making them vulnerable to warming ocean water melting them from below. The concern is that these ice sheets could reach tipping points, where ice loss becomes irreversible. Once large portions begin sliding into the ocean, they may not be able to recover even if temperatures stabilize. Scientists debate when these tipping points might be crossed, but evidence suggests we're approaching critical thresholds. The ice sheets are the sleeping giants of climate change. Their full response to warming unfolds over centuries to millennia, but the warming that triggers their collapse happens much faster. We're setting processes in motion now whose full consequences will play out for thousands of years. Sea level rise, the long tail of ice ages. One of the most enduring legacies of ice ages is sea level change. During the last glacial maximum, sea levels were 400 feet lower. As ice melted, seas rose over thousands of years. This process isn't completely finished as sheets, and glaciers continue losing mass, and seas continue rising. Current sea level rise combines two factors: thermal expansion of seawater as it warms, and addition of water from melting ice. Since the late 19th century, global sea levels have risen about 8 to 9 inches. With the rate accelerating, current rates are about 1/8 of an inch per year, but projections suggest this will increase. How much will seas rise? That depends on future emissions and ice sheet behavior. Conservative estimates suggest 2 to 3 feet by 2100. More concerning scenarios, especially if ice sheet collapse accelerates, suggest 6 feet or more. Some scientists warn that if we commit to several degrees of warming, we could eventually see tens of feet of sea level rise, though this would unfold over centuries. Even modest sea level rise causes serious problems. Coastal flooding increases, storm surge damage worsens, saltwater intrudes into coastal aquifers and farmland, Low-lying nations face existential threats. Cities like Miami, New Orleans, Shanghai, and Mumbai are highly vulnerable. The Ice Age perspective reminds us that Earth has experienced massive sea level changes before. The difference is pace. Natural Ice Age sea level changes happened over thousands of years, giving ecosystems and early human populations time to adapt. Current warming compresses similar changes into centuries or decades, far faster than societies are prepared to handle. Mountain glaciers, sentinels of change, while polar ice sheets hold most of Earth's ice. Mountain glaciers are changing faster and more visibly. Glaciers in the Alps, Rockies, Andes, Himalayas, and other ranges worldwide are retreating rapidly. Photographs comparing glaciers now to a century ago show dramatic losses. These glaciers are remnants of the Ice Age, surviving in high-altitude refugia, where conditions remained cold enough. As temperatures rise, they're melting away. Some scientists estimate that by the end of this century, many mountain ranges could be essentially glacier-free. This matters beyond aesthetics. Mountain glaciers store water, releasing it gradually during summer, when downstream populations need it most. Rivers fed by Himalayan glaciers support billions of people across Asia. Andean glaciers supply water to major South American cities. As glaciers shrink, water availability becomes more variable and uncertain. Mountain glaciers also provide early warning of climate change. They respond quickly to temperature changes, making them sensitive indicators. Their widespread retreat across the planet, in different climate zones and different hemispheres, provides powerful evidence that warming is global and sustained. The loss of glaciers represents a transition from an Ice Age world, where glaciers persisted even in interglacials due to high altitude, to a warmer world where only the highest, coldest peaks retain ice. We're witnessing the final melting of ice that has existed for thousands of years, ending the last true remnants of the Ice Age outside Antarctica and Greenland. Learning from Ice Age transitions, Ice Ages teach us that Earth's climate is dynamic, not static. The comfortable conditions we've known throughout recorded history are unusual, a brief stable period in an otherwise turbulent climate system. This perspective is both sobering and informative. From Ice Age research, we've learned that climate feedbacks can amplify small changes into dramatic ones. A slight increase in summer sunlight triggers feedbacks that grow continent-spanning ice sheets over thousands of years. Similarly, current greenhouse gas increases, amplified by feedbacks, can produce warming that persists for millennia. We've learned that abrupt changes are possible. Climate doesn't always change gradually. It can flip between states rapidly, especially when feedbacks and tipping points are involved. The Younger Dryas event, where temperatures plummeted suddenly and then rose equally suddenly, shows climate's capacity for surprises. We've learned that ecosystems are resilient but have limits. Life survived multiple Ice Age cycles by migrating, adapting, and persisting in refugia, but rapid changes cause extinctions, especially for species with specific habitat requirements or slow reproduction. The megafauna extinctions warn us that large, slow-reproducing species are particularly vulnerable, a category that includes many species today, from elephants to whales to great apes. We've learned that sea level is intimately connected to ice volume. The 400-foot sea level difference between glacial and interglacial periods reminds us that relatively small changes in global temperature, sustained over long periods, cause massive sea level changes. This isn't theoretical, it's happened repeatedly in Earth's history. Most importantly, we've learned that climate stability enabled civilization, agriculture, cities, trade networks, modern society all developed during the Holocene's unusual stability. As we destabilize climate through greenhouse gas emissions, we're conducting an experiment with the very conditions that allowed civilization to flourish. The Ice Age that didn't happen here's a fascinating what-if in the mid-20th century. Some scientists worried that human activity might trigger another Ice Age. This wasn't crazy air pollution, was injecting sulfate aerosols into the atmosphere, which reflect sunlight and cool the planet. A few scientific papers discuss this possibility. This concern was based on limited understanding and was never the scientific consensus. By the 1970s, it was clear that greenhouse gas warming would far outweigh any cooling from aerosols. But the coming Ice Age narrative persists in climate change debates, often used to suggest scientists don't know what they're talking about. The reality is more nuanced. Scientists did discuss multiple possibilities based on different factors. Once the evidence clearly pointed to warming from greenhouse gases, the scientific consensus shifted accordingly. This is how science works, following evidence to conclusions, updating understanding as new data emerges. The aerosol cooling effect is real. Air pollution does reflect sunlight. In fact, cleaning up air pollution has slightly increased warming by removing this cooling effect. But the greenhouse warming from CO2 is much larger and longer lasting. CO2 persists in the atmosphere for centuries. Aerosols fall out in days to weeks. There was never a real possibility that aerosol cooling would overcome greenhouse warming and trigger an ice age. This history reminds us that climate science has evolved through careful observation, measurement, and theory refinement. Today's understanding of ice ages, greenhouse effects, and climate feedbacks is built on decades of research from thousands of scientists studying ice cores, ocean sediments, atmospheric chemistry, and orbital mechanics. The evidence is overwhelming and consistent. A new epoch. The Anthropocene, some scientists propose that we've left the Holocene and entered a new epoch, the Anthropocene, the age of humans. The idea is that human influence on Earth is now so profound that it will be visible in the geological record millions of years from future, just as past ice ages are visible in rocks today. Evidence 4. The Anthropocene includes widespread deposition of radioactive isotopes from nuclear testing, microplastics in sediments worldwide, altered carbon isotope ratios from burning fossil fuels, species extinctions and introductions creating novel ecosystems, and fundamental changes to biogeochemical cycles like nitrogen and phosphorus. If future geologists drill sediment cores millions of years from now, they'll see a clear boundary marking the Anthropocene. Below it, natural ice age cycles with predictable patterns. Above it, disrupted patterns showing human influence, sudden CO2 increases, altered isotope ratios, extinction markers, and synthetic materials that never existed in nature. This is unprecedented. Humans have become a geological force, capable of altering planetary systems on scales that will persist for millennia. The ice sheets took thousands of years to grow and melt during natural cycles. We're potentially committing them to melting in centuries. The biological impacts of ice age transitions unfolded over thousands of years. We're compressing similar disruption into decades. The question is whether the Anthropocene will be a brief catastrophic event visible in future rocks, or a transition to a stable human-managed planet. That depends on choices we make now. Hope and action writing the next chapter. The Ice Age story might seem to suggest that climate change is beyond human control, after all. Massive ice sheets grew and melted without any human influence. But this perspective misses the crucial point: pace matters enormously. Natural. Climate changes happened over thousands to tens of thousands of years. Ecosystems migrated. Species adapted or found refugia. Coastlines shifted gradually. Early human populations moved with changing conditions. The changes, while massive in magnitude, unfolded slowly enough for adaptation. Current warming is different. We're changing climate on timescales of decades to centuries, far faster than natural ice age transitions. This rapid pace is what makes current climate change so dangerous. Natural systems and human infrastructure can't adapt fast enough. But here's the hopeful part, because human activity is causing rapid climate change. Human choices can also slow it. We're not helpless before astronomical cycles or geological processes. We can choose to reduce greenhouse gas emissions, protect and restore ecosystems, adapt our infrastructure, and transition to sustainable systems. The Ice Age research that revealed how climate works also shows us the levers we can pull. We know greenhouse gases control temperature, reduce emissions, and warming slows. We know ecosystems need refugia and migration corridors during change. Protect these, and species have better chances of surviving. We know ice sheets and sea level respond to temperature, limit warming, and we limit ice loss and sea level rise. Technology offers solutions. Renewable energy can replace fossil fuels. Sustainable agriculture can feed humanity while restoring soil and capturing carbon. Protection and restoration of forests, wetlands, and oceans can help stabilize climate while preserving biodiversity. These aren't theoretical, they're happening now, needing only to be scaled up. The long view thinking, like ice cores. Cores teach us to think on long time scales. The bubbles trapped in ancient ice connect us to atmospheres from hundreds of thousands of years ago. The layers of ice accumulated over millennia, preserving Earth's climate history with remarkable detail. This long view is humbling and instructive. From the ice core perspective, human civilization is a brief moment. The 12,000 years of the Holocene, containing all of recorded history, is a thin layer at the top of the core. Everything we consider ancient pyramids, classical civilizations, medieval kingdoms shaped within a sliver of ice representing just a few meters of accumulation. Yet in this geological instant, humans have altered the atmosphere more dramatically than any ice age transition. The CO2 increase from glacial to interglacial periods, which took thousands of years, was about 100 parts per million. We've increased CO2 by about 140 parts per million in just decades. Future ice cores, if they form, will record what we're doing. The layer representing our time will show an abrupt chemical change, CO2 spiking, isotope ratios shifting, new compounds appearing. Future scientists, if any exist, will see in that ice layer the moment when one species gained the power to alter its planet's climate. The question is what else they'll see. Will they see a brief spike followed by stabilization, showing we recognize the danger and changed course? Or will they see the beginning of a dramatic warming that persisted for thousands of years, triggering ice sheet collapse, massive sea level rise, and ecosystem disruption? That layer of ice is still forming. We're living in the time that will be preserved. Our choices are being frozen into the geological record right now. Conclusion. The Ice Age gift, we began this journey standing on a glacier 2 miles thick. In New York City 20,000 years ago, we've traveled through time, watching ice sheets grow and retreat in rhythm with Earth's orbital dance. We've seen how ice-shaped continents drove evolution and ultimately created the conditions for human civilization to flourish. The ice age cycles reveal something profound. Earth's climate is a finely balanced system, responding to subtle changes with dramatic results. Small variations in sunlight, amplified by feedbacks, have repeatedly transformed the planet. Life has endured, adapting and evolving through these cycles, but not without cost. Species extinctions mark every major transition. We are creatures of the Ice Age, evolved during climatic instability, adapted for flexibility and resilience. But we built our civilization during the Holocene's unusual stability. This stability, predictable seasons, reliable rainfall, stable coastlines, is the foundation of everything we've achieved. Agriculture depends on it. Cities are built around it. Economic systems assume it. Now, by increasing greenhouse gases far beyond anything experienced during the past 800,000 years, we're destabilizing the climate that enabled our civilization. We're not causing another ice age, we're doing the opposite, preventing the natural cooling that would eventually return while adding unprecedented warming. The ice cores show us that this isn't just about polar bears or future generations. It's about maintaining the climate conditions that make civilization possible. Every degree of warming, every foot of sea level rise, every shift in rainfall patterns makes the world less like the stable Holocene and more like the turbulent transitions between ice ages. But Ice Age history also teaches resilience. Life survived dramatic changes before. Our ancestors endured Ice Age conditions, adapted to new environments, and thrived. The difference is that we face change of our own making, which means we have the power to influence outcomes. The great ice sheets took thousands of years to grow, piled snowflake by snowflake, layer by layer. They teach us patience and perspective. The solutions to climate change won't happen overnight, but every choice matters. Every ton of carbon not emitted, every ecosystem protected. Every step towards sustainability is a layer in the foundation of a livable future. Think of it this way: Ice Age cycles show that Earth's climate has dramatic swings, but also that it can stabilize for thousands of years, creating conditions where life flourishes. The Holocene gifted us 12,000 years of stability. That gift enabled everything we've become. Now it's our turn. We can't stop orbital cycles or prevent all climate change, but we can choose whether to amplify dangerous warming or limit it. We can decide whether to protect the ecosystems that buffer climate change or destroy them. We can determine whether the layer of ice forming now records a civilization that recognized its impact and chose wisely, or one that didn't. The ice is still forming, accumulating snow that will become the ice cores of the future. The story isn't finished. We're writing it now, choice by choice, action by action. The Ice Age cycles remind us that climate change is powerful, That feedbacks amplify small changes. The transitions are dangerous times, but they also remind us that stable periods exist, that life is resilient, that Earth has endured through immense changes. We inherited a planet shaped by billions of years of geological processes and millions of years of ice age cycles. We received the gift of climate stability at exactly the right moment in human development. That gift is precious beyond measure. The question is, will we preserve it? Will we be the generation that understood what ice ages teach us about climate, that recognized the value of stability, that chose to maintain the conditions that allowed civilization to flourish? The answer is being written now, frozen into ice cores, recorded in tree rings, preserved in ocean sediments. Future geologists will read that record. Let's make it a story worth reading, a story of a species that gained the power to alter its planet and chose to use that power wisely. The ice age cycles will continue, playing out over thousands of millennia, but the next few decades will determine what world our children inherit. That's the real lesson of ice ages. Climate shapes everything. Stability is precious, and the choices we make now echo through geological time. So let's choose well. Let's honor the ice age gift of stability by preserving it. Let's ensure that the layer of ice forming now records not catastrophe, but wisdom, the moment when humanity understood its power and chose to build a future as remarkable as the 4.5 billion years of Earth history. That made us possible. The story of ice ages is ultimately a story of resilience, adaptation, and the incredible interconnectedness of Earth's systems. It's a reminder that we're part of something much larger than ourselves, inheritors of a planet shaped by forces we're only beginning to understand. And now, we're part of those forces. The ice is watching. The future is waiting. Let's make sure the story continues.